Section 1 Introduction. We're going to talk about a common issue in the deployment of large foundation models. These models are used in a variety of settings, from real-time responses on mobile phones to large-scale web services on multi-cluster GPUs. To cater to these diverse settings, each model family offers a few independently trained models of different sizes. These models are usually scaled linearly on a log scale to cover a wide range of applications. For instance, the Llama model family offers models with 7 billion, 13 billion, 33 billion, and 65 billion parameters. However, this approach has two main drawbacks. First, since the models are trained independently, they require significant overhead for collocation during inference and lack behavioral consistency, which hampers inference optimization techniques like speculative decoding and model cascades. Second, due to the training overhead, only a few models are typically trained, which may not cover all possible use cases. For example, a deployment setup might have the capacity to support a 40 billion parameter Llama model, but can only host a 33 billion variant because the next larger model, 65 billion, has significantly higher latency. This means settling for a less accurate model despite having a larger latency budget. Model compression approaches aim to address this issue, but they usually require additional training for each model that needs to be extracted. Moreover, when applied to large language models, LLMs, these techniques often significantly reduce accuracy. In this paper, we introduced MatFormer, a flexible transformer architecture that allows for training one universal model from which hundreds of smaller models can be extracted without any additional training. MatFormer is a general architecture that can be applied to both encoders and decoders, is domain agnostic, and is compatible with most design choices and training pipelines of large transformer-based models, LLMs and vision transformers, VITs. MatFormer introduces a nested substructure inside the standard transformer block, following the principle of Matryoshka representation learning. This means that each transformer block is contained within the next, with the parameters of each block contained within the parameters of the next. This substructure can be induced in both the attention and the feed-forward network, FFN, blocks of the transformer. Consider a FFN block that has a certain number of neurons in the hidden layer. MatFormer induces a Matryoshka structure on these neurons, where each block contains a certain number of neurons, with the first block containing the most significant neurons. This structure can also be applied to the attention heads and the token embedding supplied to each transformer block. However, in most LLMs and VITs, the FFN block in the transformer accounts for more than 60% of non-embedding parameters and is responsible for the largest chunk of latency during inference. Therefore, in this work, we focus on inducing the MatFormer's nested substructure in the FFN block. We then stack these individual blocks to form nested models with shared parameters, which we train jointly by combining each model's loss. This leads to a natural question: can we extract more than these nested models after inducing the MatFormer structure? The answer is yes. Using the trained MatFormer blocks at each layer, we can form new models by mixing and matching these blocks across layers, forming a large number of different models. We found that these extracted models are surprisingly accurate, with accuracy scaling with the size of the extracted model. We trained MatFormer-based decoder-only language models, MatLM, up to 2.6 billion parameters and found that a MatLMs trained with exponentially spaced granularities almost match the validation loss and one-shot downstream evaluations of the respective baseline models trained independently from scratch. B. Our extracted models using mix and match lie on the accuracy vs parameters trade-off curve generated by the explicitly trained models. C. The loss versus compute law for different MatFormer models remains similar to vanilla transformer models across different granularities. And D. The models extracted from MatLM natively have highly consistent behavior that is highly desirable for inference optimizations and deployment across scales. We also studied MatFormer-based vision transformer, VIT, models, MatVit, and found similar results. For example, MatVit L16 improves the accuracy of the standard VIT L16 model on ImageNet-1K, and the extracted submodels all match or even perform better than the independently trained baselines. Furthermore, we found that, due to high consistency, MatVit models can be used as elastic encoders for adaptive image retrieval. This means that the metric space of an image encoded by the universal, i.e., the largest, MatVit model is roughly preserved by the nested models. Hence, Based on query complexity, system load, and various other considerations, we can use one of the extracted MAT-VIT encoders at inference time for retrieval on a fixed corpus encoded by the universal model, providing over 40% lesser compute overhead with less than 0.5% drop in accuracy. In summary, we make these key contributions. 1. We introduce MatFormer, which incorporates a nested substructure within the standard transformer and jointly optimizes all the granularities to produce a single, universal elastic model. 2. We show that employing mix and match of granularities across layers in a universal MatFormer model yields hundreds of accurate and consistent models without any additional training cost. 3. We demonstrate that MatFormer generalizes effectively to both decoder-only language models, MatLM, and vision encoders, MAT-VIT, scaling as reliably and accurately as the standard transformer, while enabling significantly faster autoregressive generation and large-scale adaptive dense retrieval. Section Summary. In this section, the authors introduce MatFormer, a novel architecture that incorporates a nested substructure within the standard transformer model. By jointly optimizing all the granularities, MatFormer allows for training a single universal model that can be used to extract hundreds of smaller models without additional training. These extracted models, obtained through mix and match of granularities across layers, are accurate and consistent, making them suitable for various downstream tasks such as autoregressive generation and dense retrieval. Section 2. Related work. Let's delve into the existing work and our proposed model, MatFormer. The standard transformer model has become a cornerstone for foundational models across various fields such as language, vision, and audio. However, it lacks the flexibility to adapt to different resource constraints, which is crucial for large-scale deployment. Current solutions to this problem include training multiple models of different sizes, using efficiency techniques like quantization, pruning, distillation, and a mixture of experts with varying capacities. But these solutions often cater to a single constraint and require additional training or trade-offs between memory and computation during inference. This makes them less than ideal for adaptive deployment. Transformer-based language models are often sped up during inference using techniques like speculative decoding or early exiting. This allows for real-time deployment. There have been attempts to obtain multiple smaller models from a single model, especially focusing on CNN encoders. For instance, the OFA creates a universal CNN model used to extract and fine-tune submodels for various deployment constraints. However, these techniques are not truly flexible and require significant training overheads. Recently, some of these techniques have been extended to transformer encoders for extracting submodels in both static or dynamic settings. But they fail when it comes to decoder-only language models. On the other hand, Matryoshka representation learning and FlexiVit demonstrate elasticity in output and input spaces respectively. They can smoothly span deployment constraints with minimal overhead. Our proposed model, MatFormer, is inspired by these works. It aims to provide truly flexible and adaptive transformer-based models that can balance accuracy and computation trade-offs with minimal changes in training overhead. We also refer readers to SortedNet, a concurrent work with similar goals applied to encoders. Unlike MatFormer's joint optimization of a few nested submodels, SortedNet optimizes many sampled submodels. Now, let's discuss the structure and training procedure of MatFormer. MatFormer defines a series of transformer blocks, each one nested within the next. This means that the parameters of one block are contained within the parameters of the next block. We focus on the FFN block of the transformer, as it dominates the model size and computational cost. MatFormer introduces a nested structure on the hidden representation of the FFN block. Each nested sub-block of the transformer contains the first few neurons of the FFN. Depending on the chosen granularity, the FFN operation of each sub-block is performed on an input. The weight matrices of FFN are used in this operation, and bias terms are omitted for simplicity. In this work, we chose 4 exponentially spaced granularities with FFN ratios of 0.5, 1, 2, and 4. This means that the nested hidden neurons are of the sizes that are fractions of the total number of neurons. With these nested MatFormer blocks, we can combine them to form a MatFormer model with nested submodels. The input and output embedding matrices are shared across the models. Section Summary. The standard transformer model is powerful but lacks native elasticity for adaptive deployment across different resource constraints. Existing solutions involve training multiple models of varying sizes or using post-hoc efficiency techniques, but they are specific to single constraints and require additional training or trade-offs. MatFormer introduces a nested substructure called MatFormer, which enables truly elastic and adaptive transformer-based models that span all accuracy vs compute trade-offs with minimal changes in training overhead. Section 3.2 Training. We'll now discuss the training process for our transformer model, which we'll call M. When we input data, X, into M, we denote this as M, X. We'll also use L to represent the loss function, which measures the difference between the model's output and the target output, Y. So, L, M, X, Y, represents the loss function for our model. Our model, MatFormer, uses a straightforward training strategy. It optimizes all the G-nested submodels together. The loss for MatFormer is calculated as a weighted average of the loss of these G submodels. We use standard stochastic gradient-based optimizers for training. Each submodel is assigned a weight, lambda, which is greater than 0. In this paper, we've set all lambdas to be equal, but we've also explored adjusting these weights in the appendix to further improve MatFormer. Training MatFormer involves one forward pass for each of the G submodels. This process benefits from shared computation during backpropagation. The result is G-accurate nested submodels within the universal MatFormer model. We've found that this simple strategy outperforms various other training techniques. We've also found that we can induce the structure of MatFormer by fine-tuning, instead of pre-training models. Training MatFormer is about 15% faster than training all the transformer-based equivalent submodels independently. Moreover, MatFormer allows us to extract hundreds of smaller submodels along the accuracy vs compute curve traced by the G explicitly optimized submodels. These models emerge for free during inference and significantly reduce the training cost per model. At inference time, it's easy to extract one of the G submodels by stacking the corresponding transformer block across layers. However, by selecting different granularity for each MatFormer layer, we can generate a large number of accurate smaller models for free. We call this process mix and match. These additional model granularities, which were never explicitly optimized, perform very well. Given a computational budget, we can extract a highly accurate model with mix and match for the constraints rather than using a smaller, less accurate model or training a model for this specific constraint. We've found that a compute constraint can be satisfied by various mix and match models with different accuracies. Identifying the best mix and match configurations without downstream validation is an exciting direction for future work. During deployment, all we need to store is the single universal MatFormer model for different types of elastic inference depending on the constraints. For static workloads, where compute resources are known beforehand and the inputs remain relatively similar in difficulty, we can choose the most accurate static submodel for the constraints using mix and match. This eliminates the usage of a less accurate pre-existing model or training of a new one for the specific constraints. For dynamic workloads, where the compute resources or the input hardness change on the fly, we can use the universal MatFormer model to dynamically extract the optimal submodel. This works largely because all the extracted submodels have high behavioral consistency with the universal MatFormer model, minimizing the drift across predictions from various submodels. We measure the consistency between two generative models as the percentage of matching tokens generated by them for the same prefix or using the KL divergence of the smaller model outputs with the larger model outputs. This highly consistent nature of MatFormer results in superior inference time speedups for techniques like speculative decoding and can assist in reducing prediction drift between cross-platform deployments. We also show that higher model consistency also aids metric space structure preservation in encoder models. Section summary. The MatFormer model is trained by jointly optimizing all the nested submodels together, using a weighted average of their individual losses. This training strategy results in accurate nested submodels within the universal MatFormer model. During inference, mix and match allows for the extraction of a large number of accurate smaller models by selecting different granularities for each MatFormer layer. These additional model granularities, which were never explicitly optimized, are highly performant and can be extracted within a given computational budget. Section 4 Experiments. In this section, we'll be discussing our experiments with MatFormer, a model we've developed. We've tested it across different modalities, such as language and vision, different model classes, like decoders and encoders, and different scales, up to 2.6 billion parameters. We've specifically trained and analyzed MatFormer-based decoder-only language models, which we'll call MatLMs, and encoder-only vision transformers, which we'll refer to as MatVits. These models have been trained with 4 nested granularities across various model sizes. To ensure a fair comparison, we've also trained the transformer baseline model for each granularity across model sizes for the same tasks. Our main focus is on the flexible deployment of MatFormer-based models for tasks ranging from one-shot generative evaluations to adaptive image retrieval. We've also looked into the reliable scaling behavior of the MatFormer models. We've built MatFormer-based decoder-only language models, or MatLMs, and compared them to their standard transformer counterparts. These language models follow the training pipeline and procedure outlined by previous research. For each MatLM model, we've optimized for 4 nested granularities, represented by FFN ratios of 0.5, 1, 2, and 4. This means that only the hidden representation size of the FFN block changes. We've named these models MatLM, S, M, L, XL in increasing order of model size, with MatLM XL being the universal MatLM. For comparison, we've trained standard transformer models with similar architectures. For each MatLM, we've trained 4 separate baseline models with FFN ratios of 0.5, 1, 2, and 4. We've evaluated these models on validation loss and average accuracy on 26 English tasks. Out of these 26 tasks, we've grouped 5 tasks that require generating multiple tokens under Gen, and the remaining tasks that involve choosing an option from the input text under Rank. To demonstrate elastic inference, we've evaluated the 2.6 billion parameter MatLM models on their ability to provide models spanning the accuracy vs compute curve using mix and match and to improve post-hoc inference optimization techniques like speculative decoding to further speed up accurate auto-regressive generation. Using mix and match, a MatLM can provide accurate models for every compute constraint, not just the explicitly optimized granularities. We've evaluated the impact of mix and match on the 2.6 billion parameter MatLM and compared them to 4 granularities of the 2.6 billion baseline language model. All MatLM models perform as well as their corresponding baselines, with minor improvements and drops across the scale. Mix and match helps obtain many models on the optimal loss vs compute curve at zero cost. Moreover, downstream evaluation tasks on these mix and match models also mimic this trend. In a deployment setting that only has 55% of the required compute resources needed for the MatLM XL model, it is now possible to have a mix and match model with less than 2% accuracy drop on rank evaluations. MatLM models can speed up speculative decoding, which uses an accurate lightweight language model as a draft model to generate a few tokens, followed by verifying these drafts with a larger model. A draft model that is significantly more consistent with the larger verifier model would lead to less frequent rollbacks of the draft predictions and therefore lower latency. MatLM models can be up to 8.5% more consistent than the baselines to their corresponding XL model. This improved consistency, along with the need for only a single universal model, positions MatLM favorably to improve techniques that require draft and verifier models such as speculative decoding. Speculative decoding with independently trained baseline language models results in a speed-up of up to 10% over the standard autoregressive decoding of the 2.6 billion XL model. But MatLM-based speculative decoding is up to 6% faster than traditional speculative decoding. This additional speed-up can be primarily attributed to the more consistent nature of MatLM-based drafter and verifier models and is further boosted by the ability to share attention cache across models from MatLM, which is infeasible for the baselines. Finally, MatLM further reduces the memory overhead for inference by removing the need to have 2 models during resource-constrained deployment. Section Summary. In this section, the authors evaluate MatFormer models across different modalities, model classes, and scales. They compare MatFormer-based decoder-only language models, MatLMs, to vanilla transformer models and analyze their performance on various tasks. They also showcase the elastic deployment of MatLM models, demonstrating their ability to provide accurate models for different compute constraints. Additionally, they investigate the use of MatLM models in speculative decoding, showing that they can improve inference speed and reduce memory overhead compared to baseline models. Section 4.1.2 MatLM scales as well as vanilla transformer LMs. We've established that our 2.6 billion parameter MatLM model and its submodels are as accurate as the standard transformer language models. Now, we want to look at how well these MatLM models scale during training. We compared the scaling properties of MatLMs with those of standard transformer models, training models with parameters ranging from 78 million to 2.6 billion on 10 billion to 160 billion tokens. We found that the training of our largest MatLM models scaled as reliably as the largest standard models when we compared the loss against the number of parameters. Interestingly, this wasn't just true for the largest models, but for all the submodels, regardless of their size. This led us to conclude that MatLMs scale similarly to standard transformer models. We also found that the performance of MatLMs on downstream tasks was within 0.5% of the standard models, with the smaller submodels even outperforming the standard models at scale. However, we noted that our scaling law equation doesn't capture how MatLMs have been optimized for multiple submodels and how MatLMs and standard models of the same size have different training operations per step. We'll leave these complexities for future work. Next, we extended MatFormer to vision transformer, VIT, based computer vision encoder models, creating MatVit. This allowed us to perform tasks like image classification and retrieval more flexibly. We trained MatVit models using the same setup and optimal parameters as the standard VIT models. For image classification, we found that MatVit models were as accurate as the standard models. Interestingly, for larger models, MatVit models were up to 0.35% more accurate than the standard models for the same computational cost. We also found that using MatFormer during pre-training resulted in more accurate and flexible encoders for downstream use. We also introduced mix-and-match models, which almost matched the accuracy of explicitly trained models. In scenarios where an application can only host a 50 million parameter model, MatVit can provide a model that's 0.8% more accurate than the largest standard model with less than or equal to 50 million parameters. We also applied MatVit to image retrieval, a task that involves finding semantically similar images using representations obtained from a pre-trained encoder. Given the flexible nature of MatVit, it's a good candidate for this task. We found that submodels extracted from MatVit could preserve distances between fixed database and query embeddings across all granularities, providing significantly more flexibility. For example, with a loss of less than 0.5% accuracy, MatVit L16 can reduce compute cost by 40%. This is a first-of-its-kind result and opens up a wide variety of adaptive inference strategies for large-scale semantic search.